This, the acidity of some acid HA depends upon the stability of its conjugate base, A-. Considering starting with some acid, that acid releases a proton. If it releases a conjugate base, which is very stable, very low in potential energy, that reaction will be assisted by that negative delta H, by the exothermicity. Having a negative delta H supports the spontaneity of a process, will drive it forward. However, if there is some unstable conjugate base produced, that would require an input of enthalpy. That would be an endothermic process, and endothermic processes are not supported in their spontaneity by that endothermicity. Having a positive delta H makes a reaction less spontaneous, less likely to occur to a significant extent. So, the more stable A-, the more likely that the reaction occurs. So, what affects the stability of conjugate bases? Well, you see that A- involves some negative charge on that conjugate base. Now, oftentimes, negative charge or positive charge is relatively unstable for an atom to have. However, that negative charge is more stable if it's on a more electronegative element, which attracts negative charge towards it normally. So, considering that as we go from left to right in the periodic table, there's an increase in electronegativity, there is then going to be an increasing stability of any conjugate bases on which the negative charge exists on these elements. So it's more stable to have a negative charge on a fluoride than it is to have it on a methide. So as we go to the right in the periodic table, these anions become increasingly stable. Now, having some stability, having, say, fluoride, which has some stability, it is unlikely to react further compared to, say, methide. Having increasing stability, there's decreasing likelihood of acting as a base and eliminating that negative charge. So we have decreasing basicity as we go left to right. And in fact, this affects the types of bases which we might find in aqueous solution. Now, it's true then that methide is a stronger base than hydroxide. But why didn't we mention methide as one of the strong bases in previous lectures? Well, because methide, in the presence of water, will immediately react and form methane and hydroxide. Being that methide is a stronger base than hydroxide is, this reaction will go 100% towards the right here, producing hydroxide. So, in the presence of water, even though you might have methide, which is a stronger base, in the presence of water, hydroxide is the strongest base possible. So we don't mention things like methide, or hydride, or amide. Now, as we go to the right here, we have increasing stability of our anions, and hence increasing ability of these compounds to release protons. So HF is a stronger acid than water, ammonia, or methane. Now, as we go down the periodic table, we have increasing radius. So, for example, fluoride has a small radius compared to iodide. Now, a negative charge is more stabilized if it's distributed over a larger area. So, iodide is significantly more stable than fluoride is. Having this increasing radius increases the stability of the anions and hence decreases the basicity of these compounds. Whereas fluoride is quite unstable and therefore likely to react into hydrogen fluoride, iodide is quite stable and unlikely to react into hydrogen iodide or hydroiodic acid. So as we go down, we have decreasing basicity, or inversely, increasing acidity for those conjugate acids of these. So as we go down the periodic table, we have increasing acidity. You might recognize that hydrogen iodide, hydrogen bromide, and hydrogen chloride, or hydroiodic, hydrobromic, hydrochloric acid, these are all strong acids by definition, but hydroiodic fluoric acid is not a strong acid. And this is the reason why. And similarly, as we go down group 6A, we go from water to hydrogen sulfide to hydrogen selenide, and we have increasing acidity of these compounds as well. Now, charge is stabilized through resonance. So, if we have a resonance structure in which this negative charge is distributed not only over just the oxygen and perhaps the chlorine within this compound, but also over the oxygen, the chlorine, and another oxygen, then we have increasing stability of that negative charge. As you add more oxygens to an oxoanion, you have increasing stability of that oxoanion through the distribution of that negative charge over a larger area through resonance. So, the more oxygens, the more stability. The more oxygens, the more stability through resonance distribution of that charge. And so, if we have more oxygens on some oxoacid, then we have increasing acidity. Now, you can see that here, going from 1 to 2 to 3 to 4 oxygens, we have increasing acidity. Now, perchloric acid is actually one of the strong acids. And chloric acid is not one of the strong acids, although it's certainly stronger than chlorous or hypochlorous acid. Now, there is some significant distribution of this negative charge on this oxygen towards the chlorine, not only through resonance effects, but also through inductive effects, or the pulling of that electron density just within this bond towards the chlorine through just this sigma bond. Yes, the more electronegative the central atom is in an oxo anion, the more stable some charge is. So we can see then that we have perchlorate here, which is more stable than periodate. Hence, because of that greater stability of perchlorate than periodate, perchloric acid is a stronger acid than periodic acid. So you may recognize that perchloric acid is one of the strong acids, whereas all these other acids are technically weak. It's increasing the acidity as we have a more and more electronegative element in the center of our oxoanion. And finally, we have here, we have ethoxide, where the negative charge is on just an oxygen really here, but this is less stable than carboxylate, in which the negative charge is distributed not just on this oxygen, but also through resonance onto this carbon and this oxygen as well. And then there's even greater stabilization if the negative charge is distributed through resonance on the carboxylate group, but also it's distributed towards some electronegative elements through inductive effects. The electrons in our sigma bonds are drawn towards the more electronegative elements. So, as we go left to right here, we have increasing stability of these anions, and hence the conjugate acids are increasingly strong as well. So, trifluoroacetic acid is a very strong or relatively strong acid. Similarly, trichloroacetic acid is quite strong as well. These are stronger than acetic acid, aka ethanoic acid, and that is also stronger than ethanol in terms of acidity. Thanks for watching, guys.